So I'm going to talk about a brief about the work going on in our lab about reinforcement learning. So I'll be giving a very brief about reinforcement learning and give a brief about the different projects that are going on in our group and maybe potential for future works. So reinforcement learning is a tool of, it's a machine learning type. It involves an agent, an environment. So in this case, this particular box is an agent. So I'll go more detail in the following slide. So there's an agent that is learning to take an action, and the objective is to maximize the reward. The goal is to develop a policy. So policy is, think about a thermostat. You are getting the information about humidity, temperature, and all the things around you. And you're basically deciding how much temperature should I decrease so that I'm comfortable. So the reward is comfortability, and there's a system evolution. So the reinforcement learning decides what is the optimal policy, which in this case is decision of the temperature. And that is mapping from the states, which are the outside temperature and humidity, to my decision. So just to go into more details, there are three main components. The first is agent. Agent is the thing that is making the decision. So this part here is the agent. And then there is an environment. Environment is what is happening around you, which is labeled here as the system. And the third is the reward signal. So the agent in reinforcement learning is the decision maker, which interacts with the system. The environment is the context in which the agent operates, which can be any form of simulated game or a physical robot. The reward signal is a value that you get based on taking a certain action in a given state. And this is the feedback that you obtain based on how good the action is that is performed. So reinforcement learning comes with the exploration and exploitation trade-off. What that essentially means is, in reinforcement learning, we don't know anything about the system. So you have to give it a time to either learn the system or make decisions in the system. Learning the system is called exploration. Making decisions in a learned system is called exploitation. So there's a fundamental trade-off in reinforcement learning, which is a trade-off how much time I should be learning the system and how much time I should exploit my learning. So exploration is we try out different actions and learn more about the system and the rewards. Exploitation is I'm taking the actions given that whatever I have learned about the agent, and my objective is to get higher rewards. So we need to balance exploration and exploitation. We can spend the entire time learning about the system and then doing nothing, or we may not learn about the system and then take the decisions. I would get stuck in a very bad policy. So there are different forms of learning mechanisms for the policy. They can be broadly classified into two types. One is called model-based and another is model-free. Model-based method is I learn the system, including whatever I need about the transitions and the rewards. So I learn my entire system and then I make decision based on the learned system. Model-free methods say that I don't even need to learn about the system. I assume there is a system. I directly make decisions without fully learning the systems. So some of the key approaches in reinforcement learning that you might have heard, Q-learning, policy gradient, ectocritic, PPO, all of them are model-free approaches. There are benefits and weaknesses of both these approaches, and the choice which type of approach you should work on, model-based or model-free, depends upon the specific problem. For example, if you have a smaller setup, smaller number of states and actions, model-based actually outperform model-free. But if you have a very, very large system and you don't have enough time, then model-free work well. So there's one special case of reinforcement learning, which is typically the first case one learns about, which is called a multi-armed bandit problem. So multi-armed bandit problem are a class of reinforcement learning problems. And this can be easily explained as you have multiple options. I give you 10 choices. You have to choose one which is the best reward. The only thing is The options I give you, you don't know how much is the reward of each of them. So the reward may be a distribution. You don't know how much is the average reward. If you knew the reward distribution, you would pick the option with the maximum average reward. But now you have to learn through the average reward and then use that average reward, and that's the trade-off. This has been used in many applications, including clinical trials. So in trials, you have to basically figure out which of the medicine is the best. So you have to try different routes, learn how they impact, and then use them. So this is also like an explore exploit trade-off. Advertising, you have a bunch of ads, you don't know which one to choose. And you have to basically learn how much is the impact of them and then choose the best. Same for recommendation system, which would be the top movie that you would recommend to the users. You don't know how a user will like that movie, so you have to do an explore exploit setup. The specific term of bandits actually came from an analogy of a gambler pulling the arm of a slot machine. So you have slot machine with multiple options. Which arm do you play? You have to play to figure out how good it is. So you have a trade-off between exploration and exploitation, which is true even in general reinforcement learning. Exploration is you have to try out different options to learn their reward distributions. Exploitation is you have to choose which option is the best. The goal is to balance some form of exploration exploitation to maximize how much overall reward you obtain in a limited time. So these problems have been used widely. So there are many applications of them. So in terms of learning methods for multi-arm bandit, there are multiple ways we can model the systems. We can model it as a stochastic system or an adversarial system. Stochastic system is you are pulling an arm. The arm distribution is a random variable, which is decided by the nature. The adversarial method is where the reward distribution is actually chosen by an adversary. So there is an opponent who is trying to make actions against you, and then you have to basically choose an option which will be best. There are many stochastic methods and many adversarial methods that have been proposed in the literature. And there have been many applications. So I'll describe some of the applications of this type of system for general reinforcement learning. The first type of application we'll go over is ride-sharing algorithms. So you might have already heard about Uber, Lyft, or whatever goes in Libya. So which basically takes passengers from one place to another. So the key question that ride-sharing algorithms from the driver side has to perform is, how do we basically come up with an algorithm in the sense, which customer should I pick next, and which order should I pick the customers if I'm doing multiple customers on a vehicle at the same time, and which order do I drop them, how should my route be, and all those things. So I have to come up with an overall algorithm that improves customer waiting times, fuel consumption, and better accept rates. Accept rates in the sense that each customer, let us say, should not be waiting more than 10 minutes at its source. If it waits more than 10 minutes, then it is called that the customer should book again, which is like rejecting the customer. So we can model such a problem as a reinforcement learning problem. So we have done the modeling and applied reinforcement learning algorithms. The key thing that we see is, compared to each vehicle having a single passenger, if we can have more passengers in a vehicle, then we can have 30% reduced cost compared to a simple pooling approach. And the waiting time of passengers reduce, you get better utilization of vehicles. So you get all the benefits that you can if you use a RL-based approach, and especially the benefits could be done that if you do pooling, you get significantly more benefits. So in this plot, what we have shown is there is accept rate. The bottom one is movie, where each vehicle can take one passenger. And then there is our approach, where you can take multiple passengers. And then the third approach that we also try is multi-hop, in which each passenger can take multiple hops to the destination. So if a person is going from A to B, they can go from, so like in this figure, they can go from they want to go from one place A to a central park. They can go from A to B, and then another vehicle can pick them up from B to central park. So if you also have this multi-hop, you get even more advantages. So we explored the benefits of pooling as well as multi-hop using a reinforcement learning framework. The second application we can think of is a network routing type problem. So if you have any form of routing or resource optimization or resource allocation type problem, it is a stochastic dynamic optimization. So what you do now impacts your future. So these type of problems, optimization, stochastic type of problems can actually be modeled as a reinforcement learning set of problems. So we can use reinforcement learning, and then we can prove significant improvement compared to the state of the art. And many of these optimization resource allocation problems have also constraints. So we can extend reinforcement learning algorithms in the presence of peak and average constraints, which are the algorithms that our group has developed. We have also worked on many other type of applications of reinforcement learning. Some of them are virtual machine or container placement in infrastructure statements systems. And this is something that we are also trying to implement in Facebook or Meta systems. Then we have hyperparameter optimization in blockchain protocols, social influence maximization. So these are some of the key applications that we are working on for reinforcement learning, and there are many other applications for this type of setup. So in terms of other key problems that we are working towards, so the first problem that we are working towards is combinatorial bandits. So in the standard bandits that we mentioned, we were picking one arm at a time. In combinatorial bandit, we aim to select k arms at a time out of a total of n arms, such that the joint selection of rewards is the best. So think of an application where you are giving k advertisements on a page, and you have to figure out which k advertisements do I give to the user. Or another option being, on a social network, you have to select k users to give your items for free, such that your influence is maximized. So these type of problems could be converted to multi-arm bandit problem, but then you have n choose k arms, which are combinatorial, so very expensive to do. So we want to get them without this combinatorial explosion. So many of these problems are NP hard, so you have certain approximation factors. So we have been coming up with different type of submodular and non-submodular type of optimization problems with approximation factors and regret bounds. The other type of problem that I briefly mentioned before in the application is many of the engineering problems have nonlinear utilities like fairness type of problems, and there are constraints in every decision making. So we have been working on combinations of nonlinear utilities and constraints, and the combination in both model-based and model-free setups. The third type of problem we are working on is multi-agent reinforcement learning. In multi-agent reinforcement learning, the state space becomes exponentially large with the number of users, and they have to make distributed decision. One of the key approach used in a monotone mixing function is that you assume U is the users, that argmax of overall queue function could be decomposed as argmax over each of the user decisions. However, this is not always the case. So we have come up with Kronecker product-based factorization approaches, which provably or empirically work better than the state-of-the-art approaches. The other type of work we have been doing is multi-agent options. So options in reinforcement learning, essentially think of them as hierarchical type of system. If you have to go from home to office, you will break down the path as saying, go outside the door, go to this intersection, take this bus, or kind of a routing problem. Here in options, we basically come up with these routes of coming up with bigger level decisions and smaller level decisions, but you have to learn what are the bigger level things that you can abstract. So in multi-agent, these problems become even harder. So for example, two robots have to go to a room, pick up the box together, leave a box, then one of them turns a switch, one of them does something else, and then so on. So they have to learn all these joint options in a distributed fashion. So those are some of the things that we have worked on. So that's all I have for today. So thank you all.